Sure. Thanks, Al. So I will briefly talk about our CyPSA project, which is a cyber-physical security assessment framework. So next slide. Okay, so first the project information. We have a team of researchers from UIUC, the Oregon State University, Rutgers, and PowerWorld. The project was sponsored by ARPA-E between 2013 and just ended in August 2016, with an emphasis on tech transition to industry, and that's why we actually founded the startup, CREDC Inc., which is led now by Kate and Edmund. So the seed of the project was based on 2 research papers under the TCPG project that we worked on when I, Kate, and Matt were graduate students at UIUC with Robin, Rakesh, and Gil and Tom. One of them got awarded. It was at that phase, it was a fairly theoretical paper using Markov decision processes to analyze the security of the network. And after the graduation, we decided, okay, so now we can take these research papers into more practical settings. And that's why we started, the proposal phase and got one that worked on under the ARPA-E project. Next slide.
Hang on.
Next slide.
Hang on.
It's not working. Sorry about that, Salman.
No worries.
Why we have built in
this room. We've got to cancel PowerPoint. Oh. Go back up.
Sorry, Salman.
No worries. Take your time.
We're having technology issues.
Sounds like we have time.
And then this little guy down here.
Okay, so we have it up. Awesome. So the main motivation of this CyPSA project was traditionally power system security analysis in power system terminology security, like contingency analysis, would analyze the impact of messages and incidents against power system components. For instance, given a power system, what happens if a generator goes out? What would be the impact, and how to quantify that? These kind of analysis are traditionally done under contingency analysis term for several decades, but those analyses do not consider incidents caused by cyber-side events, cyber component failures accidentally or due to malicious incidents or vulnerability exploitations. So if, for example, the server gets compromised, what is the effect of it on the physical system, on the power system? So the purpose of this particular CyPSA project was to consider or bring into consideration those cyber incidents and in measuring the impact and prioritizing the importance or severity of cyber incidents in terms of their ultimate impact on the physical power system. So next slide. Okay, so the main high-level challenges that we face in the project was first, how to, or these are research questions also, how to ensure operational reliability given increasing dependence on cyber systems. Now that the power system is not anymore just a physical power system, it's being monitored and controlled by the control centers and substations, a lot of computing devices there. And next challenge was essentially how to understand the impact of cyber vulnerabilities on grid operations. What would happen? Can I have an analysis engine that does tell me what happens if a particular computer in my substation gets compromised, potentially? How does the grid operation get affected as a result of that compromise? And then using these vulnerability assessment analyses results to prioritize mitigation solutions or security investments like the vulnerability patching or any security protection solutions that we can deploy, how can we prioritize those based on their benefit to the system security posture in terms of cyber-physical as a security posture. Next slide. So at a very high level, what CyPSA does provide is to enable utilities with capability to inventory and analyze and prioritize cyber-physical assets. When I say cyber-physical assets, the computing devices, computers, controllers on the cyber end, as well as the physical power system components on the physical end, so that we can prioritize them in terms of their importance. And importance, I'll get into more details what I mean by importance. Essentially, what is the ultimate effect of any failure in that particular component, accidental or malicious, in terms of ultimate grid operation, the power system security. Next slide. So, being a bit more concrete, the main target application that we focused on this project, as I mentioned, was contingency analysis. Traditionally, how contingency analysis, or what-if analysis, so-called, sometimes is done is manually operators define some contingencies, some outages, N-1 contingency analysis criteria that you've heard. In a power system with N components, like N transmission lines, I want my power system to be to tolerate any single contingency, line outage in that case. So they manually define outages and contingencies, and then in order to quantify the impact of those contingencies in the power system, they simulate the power system to measure what is the impact if that contingency happens, if that outage occurs in practice, and whether my system can tolerate that automatically. And if not, essentially they rank these contingencies in the order of the severity of their impact on the power system. So essentially, if a line outage happens, if it causes overflows on other neighboring lines, then that is a safety property violation, and that contingency has to be taken care of in order to be N-1 compliant, contingency compliant. Next slide. So in this project, we essentially said, okay, now that this contingency analysis, traditional ways of doing it on the power system is in place and done, can we use this to analyze what kind of contingencies on the power system may occur if any of my computing devices and controllers, for instance, fail or get compromised accidentally, or as I said, through malicious attacks. So what is the effect of it on the physical system? That requires understanding of dependencies between cyber and physical components of the whole cyber-physical power grid. Next slide. So the way we did it was in order to understand these dependencies, we modeled the whole cyber-physical system through both cyber models, the cyber network topology, along with the firewall rule sets, gives us the attack graphs, and we use those as security-oriented cyber models. And attack graphs essentially, as I said, generated by firewall rule set analysis, as well as the cyber network topology, essentially enumerates all helps us enumerate all the attack paths on the cyber end that an attacker can take, starting from internet or any potential attack source, all the way to a critical cyber component which is connected to physical components, such as a relay. So once an attacker compromises the relay, then it may open the corresponding circuit breaker. Now, what is the effect of that circuit breaker opening on the power system side? That is done on the physical modeling aspect, that we are doing power flow models and traditional power system analysis that we'll get, actually I'll get to in the next slide. So dividing the problem, the research problem, actually it's still previous, dividing this research problem in these two aspects, the attack graph analysis on the cyber end helps us quantify and measure the ease of penetration for the attacker to start from internet to get all the way to relays or any, as I said, cyber asset that is connected to physical components, and use the power flow models and physical models to measure the severity of the ultimate impact if he or she decides to open the corresponding circuit breaker, for instance. And then develop algorithms to prioritize and rank these attack graphs, considering their ease of penetration as well as the impact on the power system. Next slide. Okay, so the very high-level pipeline or the block diagram of CyPSA is the following: that NPView from Network Perception, Robin, gives us the attack graphs based on the inputs from the cyber topology as well as the vulnerability information. So the NPView receives the cyber network topology, how are computers interconnected in my cyber network, control network, and what are the firewall policies that mandate or allow, not mandate, I'm sorry, what are the allowed communication patterns between these computers, the firewall rule sets, as well as the vulnerability information about this computer. So if the computer A is connected to computer B, and that communication between from A to B is allowed by firewall rule set, if computer A is compromised, computer B can also be compromised afterwards by the attacker who already compromised computer A if computer B has a sub-vulnerability. And those vulnerability information are automatically fetched from National Vulnerability Database to enhance the model in terms of vulnerability. So that essentially NPView spits out the attack graph, as I mentioned, to enumerate all possible attack paths in my cyber network, starting from where the attacker sits, the internet, outside of the control center initially. And then the SOCA receives this attack graph as well as the power and essentially as well as the power topology, and it iteratively communicates with power role for every attack path in that attack graph. The ultimate attack path step, if it's to compromise a particular relay, it communicates with power role, tell me what is the impact if this relay opens that circuit break in my power system. That is the impact. And NPView has already measured the ease of that penetration for that attack path, and SOCA uses these results to rank these attack paths. To actually, we have several use cases to rank assets on the cyber end in terms of their importance if the corresponding vulnerability gets compromised, and so on and so forth. Next slide. So just illustrating what I just said. Next slide. Next slide.
Next slide.
Okay, good. So NPView gives us the, this is just a bit like implementation-oriented illustration. NPView generates attack graph and gives it in XML format to SOCA. Next slide. SOCA talks to Powervault through socket communication iteratively to enhance the attack graph model generated by NPView based on the impact of those incidents on the power system if the corresponding attack graphs are taken all the way to ultimate relay phase in the substations. And next slide. And uses that analysis to feed the CyPSA web GUI that definitely, I mean, we have it working, but I'll have just some screenshots in next slide. So essentially what GUI does provide is an inventory of all the assets of the cyber end and the physical end that the operator can go through. The interconnections are viewed and all that. Next slide. The GUI also provides the rankings of the vulnerabilities on the cyber end based on the SOCA analysis. So essentially the first ranked vulnerability in the software essentially is the vulnerability that if it gets exploited, attacker will can get to the underlying relay in one of the substations easily and cause a big impact on the power system. And the ranking is done that way, and we have these rankings. Essentially, you can think of these vulnerabilities as actionable items that operators can look at and say, okay, this is the vulnerability I need to patch now because the severity of the potential impact on the power system would be huge if it gets compromised. And even like the operator can use the GUI to speculate or emulate the patching of that vulnerability and see how patching that vulnerability or taking the corresponding response action or mitigation action will increase or improve the security posture of the whole grid network. Next slide. In addition to the cyber part visualization, it also visualizes the power side that, you know, if this vulnerability gets exploited, what would my power system look like if the corresponding, for example, circuit breaker gets open ultimately after the attack succeeds. Next slide. So last two slides, I'll just talk about the advantage and use cases. Essentially, what CyPSA ultimately provides is the hybrid modeling of cyber and physical aspects together so that they can do contingency analysis considering both the physics and cyber side topology. Next slide. And the potential use cases that we used for our tech transition stage of the project, and now in the startup, I think as I mentioned, like Kate and Edmund are leading for utility operators. CyPSA does provide situation awareness by visualizing the current status of the cyber end and the ranking of vulnerabilities and providing actionable items to operators and security analysts. And also, it could be used like the way NPView is used currently by auditors in order to ensure to check for compliance for NERC type requirements potentially, so that it can be done in a more automated fashion rather than checklisting that is currently done. With that, I'll just conclude. That was a quick overview of CyPSA. If you have any burning questions, feel free to ask. Otherwise, shoot me an email and I'll be more than happy to give you a demo or discuss more details.
Thank you, Salman, and once again, thanks for hitting the high points. If people are interested in this line of research, I encourage you to talk to Salman or let us email us, and we'll get you in touch with them. So now we're going to hand over to.
Yeah,